Hi students, 8.6, and to begin with I want you to look at Mr. O'Sullivan, who's on a run again. Spend a couple of minutes using the same techniques as yesterday, and I want you to see why they don't quite work. Spoiler, they don't quite work. So don't worry if you don't get to a solution, but have a little go, spend a couple of minutes on it, and then we'll go through it together. Okay, so what hopefully you noticed there is in that question, which is the same one as the first example here, the expression for acceleration is given in terms of velocity. And so what we're going to do is use something that we have looked at before, which is an alternative form for the acceleration, so that it can help us where we've got expressions in terms of velocity or in terms of displacement x. So if we know that acceleration is dx by dt, but that would be the same using the chain rule as dv by dt, and that would be the same as dv by dx times by dx by dt, and dx by dt is just the same as velocity. So I can write the acceleration as v dv by dx, and the basic reason why we might do this is because this expression doesn't involve t at all, and we don't even need to think about time. We can solve a problem using kinematics just in terms of velocity, acceleration, and displacement without considering time at all. The second one, this is the most useful one and the one you'll use most often, but there is another form which occasionally is useful, and that's to recognize that acceleration is d by dx of a half v squared. If you differentiate this with respect to x, you're going to get v times dv by dx, which is this form here, and so occasionally this form with the derivative of a half v squared is going to give us the fastest way to get to a solution. And so the examples today look at occasions where we might use one of these forms. So in this first one you looked at already, what you'll notice is that time is measured nowhere, and even in the initial conditions it's saying find his position when his velocity is a certain value. So that's a statement that relates position and velocity, no mention of time. That is the giveaway that we're going to use one of these forms. So what we do is we say, okay, we know acceleration is 1 plus v, so that means v times dv by dx equals 1 plus v. And now I've got an expression only in terms of v and x. I can separate variables and solve the differential equation. So that's v over 1 plus v dv equals the integral of 1 dx. So in other words, x, integral of the right hand side, equals the integral of 1 minus 1 over 1 plus v dv. Notice a sleight of hand here. The relationship between 1 plus v and v allows us to rewrite it in this form, so that now I can integrate 1 and I can integrate 1 over 1 plus v quite easily. So if I do that, I'm going to get v from the 1, and I'm going to get minus log base e magnitude of 1 plus v plus c. So here's my expression. I'm going to take it back to the initial conditions, which was that when he left home, he left with a velocity of 1 meter per second. And I'm going to substitute that in. So 0 equals 1 minus log of 1 plus 1 is 2 plus c. So c is log 2 minus 1. which tells me that x is v, and now I'm going to combine the logs. I've got log 2 minus log of 1 plus v, so that's log of modulus 2 over 1 plus v, just putting those together, and then I've got minus 1. So that's my overall expression for displacement in terms of velocity, and then it asks for the velocity when x equals 8. So x equals 8, substitute it in, add the 1 to the other side, and we get, it's my mistake, the velocity equals 8, so x equals 8 minus 1 is 7, 7 plus log base e of 2/9. And I'll leave it up to you guys to put that into your calculator and work out exactly what the answer is. And now I realise, it's been a while since I've made one of these, that I haven't scrolled the video down at all, so apologies for that. Leave it on here for a moment, you can see all my working out. Okay, must do better. Next one. This is an example of how the second form can be really helpful for solving a problem really quickly. So that slightly random one, the d by dx of a half v squared, I want you to see if you can apply that to solve this question really quickly. Have a go. Alright, assuming you paused the video and given it a good shot, what I'm going to do is I'm going to remember that the acceleration is d by dx of a half v squared, and then I know that v squared is 4 minus x squared in this case, so that means the acceleration is d by dx of dividing this by 2, 2 minus a half x squared, and then differentiating that with respect to x. d by dx of 2 is 0, minus a half x squared. If I differentiate that and multiply by 2, I'm going to get minus x. So this tells me that the expression for acceleration is actually just minus x, which means that when x equals 1, the acceleration is minus 1 meters per second squared. So super straightforward, but only because we knew to try this form, and the clue here is the v squared. Here's our clue that this second form might be useful. I'm just going to put an or in here because a kind of second approach, and the clue was up the top where it said implicit differentiation. Second clue which second way which we could have done this is just to take both sides of this equation, v squared equals 4 minus x squared, and then just to differentiate both with respect to x. So if I do d by dx of v squared, and then I look at d by dx of 4 minus x squared, so implicitly differentiating both sides, on this side I'm going to recognize that that is just double the acceleration. And on this side, as I differentiate that, I'm going to get minus 2x, and then that's going to tell me that a must be minus x in the same way. So slightly different plan of attack, but same result, and still using the fact that we know that acceleration is a half d by dx of v squared. Okay. Final example then for today, and this one's a meatier one. So give yourself a little bit of time, and there's two parts. We've got a helicopter hovering above the ocean. We know from scanning this question that there's no mention of time at all, and it's saying find the velocity of the object when it hits the water. So you've got this relationship between velocity and displacement. So with that in mind, try this question, give yourself a good 10 minutes, unpause the video, and then I'll go through it for you. Okay, so hopefully you've had a good go at this, so I'll go through it quite quickly. What I'm going to use here as my starting point is the fact that we know that for part A there's no air resistance, so the only thing impacting acceleration is gravity, which means the acceleration, or in other words, the second derivative of x with respect to t, is minus 9.8. So then using this form, remember I don't really want to use t because it's got nothing to do with this question. V times dv by dx is minus 9.8. Rearranging, separating variables, the integral of v dv is the integral of minus 9.8 dx. So a half of v squared is minus 9.8 x plus c. And then substituting in the fact that we know that at the beginning the height or the position is 1,000 meters, but the velocity is 0 because it's just dropping. And so substituting those in, v equals 0, x equals 1,000, that's going to tell me that c is 9,800. And so putting that in, multiplying by 2, and then doing the square root, we're going to get an expression. You could write it in a number of ways, but the expression is going to be v equals the square root of 19,600 minus 19.6x. And then if we substitute in x equals 0 to figure out the velocity when it hits the water, then the velocity is going to be, I'm just going to add in a plus or minus here because when we take the square root it could either be positive or negative. The velocity is going to be plus or minus the square root of 19,600, which is plus or minus 140 meters per second. At the beginning here I made a choice when I said that g is minus 9.8 that I was still defining let upwards direction be positive, which means just when I make this decision at this point I've got to say that the object is falling. And so the velocity is negative, therefore the velocity is minus 140 meters per second. Okay, so bear that in mind. There's no air resistance, it's falling from the helicopter, it just accelerates, and it hits at minus 140 meters per second, so incredibly fast. And of course that's not really practical because in real life there is air resistance, and so what we're going to look at in the second bit is, well, what effect that has, and it's really striking. So this time we are considering air resistance, and so our expression for acceleration, v dv by dx, is not only going to be minus 9.8, but it also has a 0.2 v squared, and this is positive because air resistance always opposes motion, so air resistance acts upwards. So here's my expression. I do the separation of variables again, and as I do that I'm going to get the integral of v over 0.2v squared minus 9.8 dv equals integral of 1 dx. So in other words, x equals, and as I'm looking at this integral here, you can multiply by 5 first of all. So this is the integral of 5v over v squared minus 49, I believe, dv. And then as we integrate this, what we notice is that the numerator is very close to the derivative of the denominator. So thinking back to when we did our calculus, this is going to be very close to the natural log of the denominator. But we need to balance the coefficient. So if I think, is it going to be close to log of v squared minus 49? Well, if I were to differentiate this, I would get 2v on the numerator. Instead, I've got 5v. So what I need to do is multiply by 5 over 2. So this is the correct integral, but of course I also need a plus c. So x is 5 over 2 log of modulus of v squared minus 49 plus c. Then initial conditions, when x equals 1000, v equals 0. Substituting that in, I'm going to get log of 49 here. So I think you end up with c equals 1000 minus 5 over 2 log base e of 49. And then when we combine that with this expression, we put it together, we can combine the logs again. We're going to end up with x equals 1000, and then both of these logs have the same coefficient, so I'm going to bring that inside, and I'm going to have plus log base e magnitude v squared minus 49 on the numerator over 49, and then the power of that is going to be to the power 5 over 2. So slightly complicated expression here. X is 1000 meters, which is where it starts, then plus the log of magnitude v squared minus 49 over 49, power 5 over 2. So initially the velocity equals 0, which means that this expression is going to be negative. So if I want to remove the magnitude sign, I'm just going to reverse this around. And then if I substitute in x equal to 0, and rearrange it, what we're going to get, and I'll leave you to I'm running out of space here, so I'll leave you just to work through the arithmetic, but what we're going to get is that v squared is equal to 49 times 1 minus e to the power minus 1000. That comes from raising both sides to power e as I invert the log, and then this exponential is to the power 2/5, coming from the 5 over 2. So then when I apply this power to this, what I'm going to get is 49 times 1 minus e to the power minus 400. This expression is very close to 1, so we're going to get v squared is very close to 49. And then you guys might have been familiar or heard of this idea of terminal velocity before. What this means is no matter how far this thing now falls, the velocity isn't going to go past 49. Sorry, square root of 49, in other words 7. So no matter how big I make x, here x is 1,000, if I drop it from a bigger height, a bigger height, a bigger height, then I'm still going to get the same overall expression, and because this thing is tending towards 1, the maximum value that v is going to take is 7 or minus 7. So v squared is approximately 49, which means v is approximately minus 7. It's falling, so negative. And so when we introduce this this air resistance, and we say that that is proportional to the velocity squared, which is realistic, what we end up with is this pattern where the velocity has an upper limit. Doesn't matter how high the thing goes, the velocity is going to level out at minus 7, which is obviously much smaller than the answer we had for part A, which was minus 140. Okay. Well, those are the examples. Last thing I want you to do just before we break is I just want you to look at the last little question on the screen. Demonstrate that you've got this topic and you understand it before you go on to the exercise. So spend a moment, have a go. I'll reveal the answer in a second. Okay, let's have a look. I'll show you the answer. I've not looked at it yet. The answer is D. So congratulations if you got that. If you didn't, take another look at it. And if you have any questions about this topic, of course, let me know before the weekend. I'll catch up with you on Monday morning, either like this or in school. All the best.